about that. Okay, so we are studying this recursion relation for positive integer s, and one can just go ahead and solve it. One can write down solutions for these little QSs. They are constructed like last time. They will have a piece. One has to first solve that recursion relation in terms of C and N, the variables on the gravitational phase space. Then one can take this limit and truncate it to quadratic order in C and N. So in general, these are going to be nonlinear quantities. They are going to be polynomials in C and N of degree, roughly speaking, s divided by 2. So the degree of the polynomial scales with s. So one truncates them to quadratic order in C and N, takes the limit u goes to minus infinity, because this is what we saw last time, gave rise to charges, at least in the s equal to 0 case. And then once one has these objects, one can impose. There is one step. We saw that for s greater than or equal than 1, these formulas were divergent. We can remove those divergences and then apply a matching condition. Like we did very explicitly in the last lecture. And what one finds quite remarkably is that one can recast the conservation law. So this leads to a conservation law in the sense that one can write down some kind of commutator of these charges with the S matrix with vanishes, whose expectation values, whose matrix element between in and out states, or the conservation law turns out to take the form of a soft theorem again. So we get a formula that looks like this. Limit as omega goes to 0 of d omega to ds omega out a omega x hat x in is equal to, again, some s out s equal to in. For higher s, this factor is increasingly complicated, but one can write it down very explicitly. And what one sees here is that on the left-hand side, what does the left-hand side mean? Well, first of all, it's a limit as omega goes to 0, so it's some kind of low energy limit. And if one imagines that we allow for A to have an expansion in powers of omega, like we did, if you remember, in the first lecture, there is a pole, there is a leading order pole, that's the Weinberg pole. This gets removed by multiplication through omega. For s equal to 0, we just get the Weinberg soft graviton theorem. But for higher s, we see that this operator, it just requires very little bit of thinking. This operator just picks out the s subleading term in a small omega expansion, right? So if you remember, in the first lecture, we talked about some ms operators. And this is exactly what appears now on the left-hand side. So these are just some kind of subleading modes of the soft graviton to arbitrary order in a low energy expansion, assuming that there are no log terms and so on. So yeah, we can discuss those later. Actually, we won't be discussing them very much in these lectures. But OK, so assuming that, on the left-hand side, we have a mode of a subleading soft graviton. And on the right-hand side, we have some formula that relates that to the scattering amplitude without that mode, without the graviton itself, up to some factor, okay, which is a generalization of the leading, subleading, and subleading soft factors. Yes?
So this derivation is like, it uses these space techniques you mentioned, right?
Yeah, so all it uses is this Ashtekar bracket, so this commutator between C and N.
Yeah, then like, is there a way to see like whether there is a universal like sub
I'll comment on that. Yeah, I'm going to tell you what the status is of all of these things in a moment. Okay. So this is one thing that you can deduce from that recursion relation. The other thing that you can deduce is that the algebra before holds at least for the linearized charges. So when I say linearized again, it's meaning like restricted to linear order in CNN. Sorry, not restricted to linear, sorry, I should say restricted to quadratic order in CNN. But actually that turns out to give, up to quadratic order, but looking at just the linear component in that bracket like we have here. So the superscript 1 means that we are projecting onto the linear component of this bracket. But to obtain that linear component, you need to take the quadratic charge and compute the commutator with the linear charge. Okay, so the Q2, the quadratic charge is actually involved in that computation. So, yeah.
Excuse me, I'm confused about some notation. You know, you have different s here. The little s is the integer, and what is the meaning of the first factor on the right-hand side? Is it a number or this capital S is superscript?
Yeah, so that's going to be a differential operator that acts on the amplitude. But it's completely determined by essentially the commutator of the truncation of this QS to quadratic order with the asymptotic particle states. And that one can compute it very explicitly, just using basically the commutator of CNN. Yeah.
Okay, so this is a differential operator which depends on the integer, little s.
So this is the differential operator that depends. So yeah, indeed, for different values of, so it's going to have more terms as s increases. But those terms, I mean, we are going to see that this is sort of some universal component of the soft theorem, of some notion of soft theorem for increasingly subleading modes of the graviton. But of course, it's not the full story. I'm going to say something about that in a moment. Okay, so this algebra that we have on the other board actually continues to hold for all s, for all positive integers s. And so for such a tower of charges s, this algebra actually has a name. So it's called the W1 plus infinity algebra. So these first appeared in the context of two-dimensional conformal field theories, where one has a stress tensor. One can think about that as an S equal to 2 current. And then there is actually a W1 plus infinity algebra occurs when you happen to have some tower of higher spin currents in a CFT. Okay. Together with also an S equal to 1 current. So this is why it's called 1 plus infinity. Okay, so this is pretty nice. You can check out for details. You can check out. So I will put references on the website, but here is one. Yeah. Sorry, there is a question? Yeah, exactly. That last time was only up to s equal to 2, but actually it turns out that that set of differential equations using the same construction turns out to imply an algebra for all these s. Okay, so this is just a formal, you can think it's just a formal mathematical exercise. It's a curiosity at this point. We have some tower of equations and it implies this algebra. But so you may wonder, what is the relation to gravity? So in particular, why should there be, like, we saw that those are equations that come from Einstein's equations for s equal to 0, 1, and 2, but how do they actually appear? Are they actually can you find them from an analysis of Einstein's equations? So what turns out to be the case is that for S greater than 2, those equations appear if you continue expanding the AB components of Einstein's equations to all orders in 1 over R. So we take the GAB equal to 0 equation. So remember, these AB indices ran over Z and Z bar. And expand to all orders in 1 over R. So to remind you, the S equal to 2, 1 came from order 1 over R squared. So now you can go to order 1 over R cubed, and so on. And it turns out, so naively you think, okay, maybe this is going to become increasingly difficult to do, and indeed that is true. But what you can show, you can prove that if you linearize, if you take these equations to all order in 1 over R and linearize them, then one can prove that you get out exactly the linearized component of that equation. Namely, you get du of Qs is equal to d Qs minus 1. And this result was actually known well, one has to do a little bit more repackaging, but you can extract this result back from papers by Newman and Penrose in the 70s. One just has to do a little bit more massaging. And the reason why it's so easy to analyze these is that it turns out that these equations just come from a 1 over R expansion of the Bianchi identities in gravity. Okay, so this is nice. Yes.
Say expand the equation in all orders, it means you're expanding your metric ansatz to higher orders in 1 by R and putting it back in the equation, getting more degrees of freedom. Like, what would be the map of QS?
Yeah, I'm gonna, you cannot do it in, yeah, exactly what you are saying should be the case. You have to continue building the metric to increasingly subleading orders in 1 over R, and at every consistent, you have to impose Einstein's equations order by order in 1 over R. But it turns out that the Newman-Penrose formalism actually allows you to simplify things a little bit. And in particular, one of the Newman-Penrose equations determines the evolution of the Weil tensor component that is responsible for these QSs. And that particular one, as you expand in 1 over R, you can manifestly show that it will take that form. So there is many things, and yeah.
But also, it seems like, so Bianchi identities are geometric things, right? They don't have anything to do with GR. It's just
It's a property of, yeah, I agree with you. And somehow these structures appear from the 1 over R expansion. If you just, I totally agree, if you took Bianchi identities and you didn't expand it, those are just things that are true. They're always obeyed by the curvature invariants, right? But actually, when you start expanding them in 1 over R, there turns out to be the structures. But it's still a little bit mysterious, I mean, at least to me, yeah, why that happens.
So in Newman-Penrose, what we usually do is also you make use only of Bianchi identities, but only you, at the end, you substitute R mu nu to be some T mu nu and try to do these things. But we don't do anything like that here, you're saying. It's purely Bianchi identity.
For these particular, I mean, because this GAB,
oh yeah, there is no T mu nu.
First of all, there is no T mu nu. Yeah, it's GAB to 0, and it's just one particular. Okay, so GAB to 0 is not just Bianchi identities in general. This is the second thing I was going to say. So now, so I started with the thing that you can prove. You can prove that the linearization of that is an equation of motion in general relativity. That's a fact. Now, the second thing that you can show is that for S equal to 3, one can also prove So s equal to 3, you can just do it explicitly. You just need to go to one subleading order in a 1 over R expansion. And this was done in a paper by Roman Rusiconi and collaborators. It's in an appendix. Again, one has to massage a little bit the results, but one can prove that that equation is still exact. So let me not write it down again, but just say that this equation still holds. Okay, and then for s greater or equal than 4, actually the right-hand side of that equation star is going to start receiving corrections, as you would expect. And I'm not going to say anything more about them because they are not really understood. So there is no real, there is no way to nicely repackage, no known way to this moment of nicely repackaging all of these corrections. So there will be higher order in C and N, and they will mix with C bar and N bar as well. And okay, there is just no known nice things going on. Although some analysis to all orders have been performed for the analog of this problem in Yang-Mills theory. So there are similar structures there that I'm not going to have time to discuss, but there has been some recent progress in identifying these corrections to these equations in Yang-Mills theory, classical Yang-Mills theory.
Sorry?
Yes?
Just to confirm, in point A, the second term you've lost by linearizing.
That is correct. The second term would be quadratic, so you'd throw it away by linearizing. Okay, so what is the status? So first of all, point B, the fact that this equation is actually exact for s equal to 3 is kind of surprising because it suggests that there is a tree-level universal sub-leading soft graviton theorem. And that has not really been discovered so far. So there is an s equal to 3 sub 3 leading soft graviton theorem. And the challenge for you guys is to find it maybe from amplitudes. The methods used by Cachazo and Strominger, and also others later on, BCFW method expanded in the soft limits, actually don't have this correction actually under control. But there should be, it seems like there should be such a theorem. Okay?
What are the observable transform under this infinity algebra? There is a representation of this W1 plus infinity?
Yes, that's right. So the Qs themselves are observables that would transform under these representations, and the Qs are in one-to-one correspondence with subleading terms in a 1 over expansion of a particular component of the Weil tensor, and these things have been related. I was going to maybe mention that or not, but thank you for the question. They have been related to multiple moments of the gravitational field. So
is that analogous of non-vectors? Because there's a huge number of non-vectors.
from a CFT point of view, you mean? I don't know, but maybe we can talk about that later. I'll say a few things at the end about how to identify these things from a 2D CFT point of view. Okay. So Okay, so that's one point. The second point is that C, so the fact that for S equal to S greater or equal than 4, that right-hand side receives corrections, basically, we just don't know these corrections, these classical, this should be some sort of classical soft theorems. That are not understood or studied really so far. Or maybe have not yet been worked out, but maybe there is a way to maybe do this from amplitude's point of view as well, and related to maybe whatever the corrections would be that appear in these equations. Then you may ask about quantum corrections. And those are really largely an open problem. And as far as I know, so all we know, I mentioned this before, is that the sub S leading soft graviton is S loop exact. But even when you go to S equal to 1, the quantum corrections, this one loop correction has not fully been worked out. But the sub S leading soft theorem should be S loop exact. So if you compute, so at every subleading order, you only have to compute the diagrams to S loop order to figure out what the full result is. Yeah.
So just to clarify what the statement is for B, there is a proposal for the S3 soft factor, or is the matching condition not?
There is a proposal for the S equal to 3 soft factor, but it has not been proven that that's the only 3-level contribution to the soft factor, which also applies to all higher S orders. But this tower of soft factors, we'll see in a moment, I mean, it's in some sense universal because it's determined by symmetries, but the sense in which this, so I'm taking universal here to mean implied by symmetry, but from an amplitude's point of view, there is no reason already at 3 level for S equal to 3 to separate out this contribution from any other order omega squared contributions that you would get in an expansion of the soft graviton.
So this is not a complete contribution at that order in omega?
No, but these equations imply, through the fact that they're not corrected through the at the S equal to 3 order, they imply that there should be an exact 3-level soft theorem to sub leading order. So this seems to be making a prediction of that fact that one still needs to compute or rediscover from an amplitude's point of view.
Do you know if it's been checked in any examples? Like maybe it's not known for all multiplicities, but like for specific amplitudes that have been seen?
I don't think this thing has been seen from amplitudes, but I may not be aware of. As far as I know, it has not been seen from amplitudes. But it should be true because otherwise there's something, wrong with either the way we compute amplitude. There's probably something wrong with the computation of the amplitudes because this is definitely, well, this tower of equations is implied by Einstein's equations. So 3-level observables in gravity should correspond to classical observables implied by Einstein's equations. So, yeah. Yes?
Is it true that only that higher order corrections you only know how to calculate perturbatively, and they altogether not known, and there is no kind of non-perturbative generalization of that algebra?
That is correct. Yes. Yes, there is no non-perturbative generalization of this algebra, but you could maybe try, like one thing that one maybe can try to do from a if gravity-minded, can try to start from this algebra and find all allowed quantizations and then declare that this should somehow control non-perturbatively dynamics in gravity. But I don't think this has been being realized, this idea. Okay. So I have some further small comments. I'm not going to write them down, but as I said, the linear term in this equation, so basically this left-hand side is related to these MS operators that we introduced in the first lecture, and we said that insertions, one can hope that these insertions, we mentioned that these guys are in some sense primaries with respect to SL2C. So this means that they should be operators in a two-dimensional, primary operators in a two-dimensional conformal field theory, whose insertions into correlation functions involving other operators should somehow be fully determined by this W infinity symmetry. And we're going to see in a moment, hopefully by the end of today, why that is the case. So here the only input, just to remind you, the only input to get all of these results was gravity and Lorentz symmetry. And we're going to see this also from a dual 2D CFT point of view by the end of this lecture. And then the second comment is that this GAB, so if you remember, and I got some questions before, in the first lecture I talked about this Hamiltonian and momentum constraints, and some people asked me, why am I talking about it? So first of all, these GUU and GUA equations are like the momentum constraints for the Cauchy slice. There's a GAB equation. You may think that maybe it's related in some sense to the Hamiltonian constraint. The reason why I'm saying that is because you see, this GAB equation for S greater than 2, I haven't proven it, but I claim that it relates increasingly subleading components of the GAB metric in a 1 over R expansion to more leading ones. So this suggests that somehow this GAB allows, like, equations has a component that implements radial evolution into the bulk. So this has not been analyzed very much before, but it would be very nice to establish a connection between this sort of Bondi gauge and quantization that one does with in this particular gauge to this more general, to this Hamiltonian formalism. And there might be interesting connections, perhaps to bulk reconstruction in the context of gravity in asymptotically flat spacetimes. Okay, so any questions? Because now for the remaining hour, I'm going to try to say some things about the CFT, the dual CFT picture to all of the stuff that we discussed before.
It's more like 42 minutes to say.
42, okay, 42 minutes. So, okay, so perfect. So far, what we have, so we just started from 4D Lorentz symmetry. So this is SO 3,1. And through these commutators of these charges, we have seen that actually the symmetry is enhanced to 2 copies of the Virasoro generated by QS equal to 1, and also these other Q bar charges. We haven't introduced them before, but we said that they exist because there is a ZZ and Z bar component. Okay, so this is a subalgebra inside this extended BMS algebra. And then through the existence sort of this approximate S greater or equal than 2 charges for all S, there seems to be some approximate W1 plus infinity symmetry also generated by QS for positive integers S. And sorry, so I forgot to mention, from a gravity point of view, this W1 plus infinity is known to be a symmetry of self-dual gravity. And recently, there's been this connection between this area-preserving diffeomorphisms in a twistor construction of twistor sort of representation of self-dual gravity. There is a relationship between that and this W1 plus infinity symmetries, commutation relations that they find here from just a more sort of like a bottom-up point of view. So there is connections between those two, and there is references that I can point to if you are interested in how to establish that connection, and those are just from the past year or so. So this is really quite recent. Okay, so we have this, we seem to be finding these more and more symmetries, but we also said that these W1 plus infinity symmetries appear in 2D CFTs. So one question that you can ask is how do 2D CFTs encode for the scattering amplitudes? So in particular, 2D CFT correlators, how are those related to for the scattering amplitudes? And to start making that connection a bit more precise, one can start with the quantization of a free field in four-dimensional Minkowski space. So consider a free field in four-dimensional Minkowski space. So this is 101 QFT, and we've written this also before, but let me just write it down again, just to remind you. We have some field in the bulk that obeys the equations of motion. So this solves box phi minus m squared phi is equal to 0. And one can take a Fourier transform, of course, as usual, as this equation and expand this bulk field in Fourier modes. So we have d3p e to the minus ipx cp star plus e to the ip dot x cp, where, as usual, p squared is minus m squared. Remember, I'm working in mostly plus Minkowski metric conventions. And in quantum field theory, one just simply promotes, so this is just a classical free field in Minkowski space. These coefficients are arbitrary. In quantum mechanics, one promotes them to operators and demands that the vacuum is annihilated by the negative frequency modes. So in QFT, promote CP and CP star to operators. So essentially creation and annihilation operators, AP dagger. Okay, and we build our asymptotic states, as I said, from a vacuum, from the Minkowski vacuum that is annihilated by all of the A's. And then these incoming, so a one particle state is obtained by acting on the vacuum with the creation operator. Now, a small note is that the reason why so a small note is that, of course, these plane waves are solutions, form a basis of solutions to the Klein-Gordon equation. So e to the plus minus ip dot x are a basis of solutions to the Klein-Gordon equation, which of course is manifest by the fact that I was allowed to write any solution, any bulk field X, as a linear combination of these plane waves. Now, the point is that, of course, this is not the only basis that one can write down, but it is a preferred basis using quantum field theory because it diagonalizes the asymptotic momenta. And this is done this way because usually our asymptotic states organize in Poincaré representations, and the starting point for constructing Poincaré representations is to choose eigenstates of the momentum operator. So, so in particular, you can think about, I should say, that what is the Klein-Gordon equation? It's just the Casimir for the Poincaré algebra. Sorry, for m equal to 0. So we have, this is one of the two Casimirs of Poincaré. And e to the, quite obviously, e to the plus minus ip dot x diagonalize the momentum operator p mu. But since we have seen that this Lorentz algebra was so important, because remember, to see all of the symmetry structures, we really started from this notion of space-time primaries that transform nicely under Lorentz symmetries. Perhaps it may be more useful to reorganize the asymptotic states. Well, ultimately, we want to organize our asymptotic states into representations of whatever the asymptotic symmetry algebra is. So here, at least, we know that there is this extended BMS algebra, so we might want to organize our asymptotic states into representations of the extended BMS algebra. Unfortunately, in 4 dimensions, these representations have not been classified yet. In 3 dimensions, there is some work. Those are classified, and then one can exploit those tools. In 4 dimensions, the story is not completed. So one may want to make as much symmetry manifest as possible. So we might want to make, we see that there is some glimpses of this W1 plus infinity algebra. So we might want to organize our asymptotic states into representations of those. So, so more basically, at a more basic level, one can try to organize asymptotic particle states in Lorentz representations instead, or SL2C representations. So these are, of course, smaller than the Poincaré representations, but they will be more useful in making more of the symmetries manifest. So if one tries to do that, this plane wave basis suddenly becomes not so useful anymore. So the idea is that we discussed this a little bit in one of the previous lectures, but in SL2C has 2 Casimirs. So roughly speaking, from bulk point of view, we have a boost towards a particular point on the sphere, and we have rotations around that point as well. And those 2 commute are operators that commute with one another. So we want to find a basis of wave functions that diagonalize these SL2C Casimir elements. Sorry, Cartan generators. I misspoke. Cartan generators. Also the Casimir, but yeah, just like we construct SU2, yeah. So these would be, so a choice could be boosts Ki towards a point z bar, and rotations boost not ki, but rather k3, and I'm choosing my axis to point in the z bar direction, and then we have the corresponding rotation generator around the same axis. Sorry. All right. So
So SF2C is also infinite dimensional representation. We are only considering the finite dimensional with
we will come back. Yeah, we are. Sorry. These representations I'm talking about, so we will see later on that the representations that will allow us to recover this W generators are some finite dimensional representations, but you're totally right. I'm going to be agnostic so for now on which representations we want to look at. In general, we want to look for we would want to look in CFTs. Usually we care about highest weight representations. Those are not finite dimensional, right? So we want to see whether we can construct highest weight representations. Yeah, just a moment. I'm gonna, so far I haven't said which representations, but I will impose that in a moment. Okay. So we want to find the basis of wave functions that diagonalize these boosts and rotations around the point, z and z bar around the direction in space-time. And you see immediately that these plane waves are not going to be, not going to satisfy this property. And there is a simple reason for that, which is that momentum generators don't commute with boosts. And of course, you cannot construct simultaneously a momentum eigenstate and the boost eigenstate. So K3 is not proportional to Bx. But how can we construct such a basis? So we still want to solve the equations of motion. So we still want to solve the Klein-Gordon equation. We just want to find particular linear combinations of these plane waves that, I mean, they form a basis. So we should be able to take some linear combination of these guys that diagonalize these boosts. So this is something that people have done in a variety of contexts. So one demands that, so look for a basis of solutions to the Klein-Gordon equation. This would be for scalars. But people have done this also for your favorite like bosonic particle or even fermionic particles, and you can also do it. Yeah, you can do it for helicity, for photons, gravitons, and so on and so forth. So it has been done for other types of fields too. But I'm just going to, since it's simplest to talk about scalars, I'm just going to talk about those. So we want to look basically for solutions to the equations of motion, whatever those are, that has the following properties, that diagonalizes J3 and K3. So basically, this means that K3 acting on some psi that's, again, just like the plane waves are. They're going to be functions of some bulk point x and some boundary momentum p that diagonalize boosts with eigenvalue delta. And for scalars, we also want that J3 annihilates this guy. And in the original paper, well, in one of these papers from 2016 by Pastersky, Shaw, and Strominger, it was also demanded, and this now addresses one of the questions that was asked before. They also demanded that these solutions are highest weight with respect to the Lorentz algebra at z equal to 0. So this condition was inspired by the standard condition that one uses to construct representations of the 2D conformal algebra. So these conditions look something like this. So L1 acting on psi delta is L bar 1 acting on psi delta is equal to 0, where since I've just been referring to the Lorentz algebra, these L1 and L1 bar are just going to be some linear combinations of the the boosts and rotations around axis perpendicular orthogonal to the one that we've chosen to diagonalize. So these are linear combinations of J1, J2, K1, and K2, and you can find, I think I gave one exercise earlier on, so if you have done that, you would know exactly what I'm talking about. But if you haven't, then you can read about this in lecture notes, and there have been various lecture notes on the subject. Okay, and these are just some differential equations that one can solve. And it turns out that the solutions take the following form. Yes?
Are we getting the P labels? These are just solutions of like Gordon equation. What is the P there?
Yes, exactly. So the solutions are going to be parametrized by the on-shell momenta. So just like plane waves are parametrized by an on-shell momentum P, in the same way here these plane waves are going to be parametrized by an on-shell momentum.
That's what delta would do, right? Like you want to...
I see. You are asking, the question is, it seems like I have more degrees of freedom than originally started with. Great. So I should say, so to fix that, for massless particles, I really want to write, I am going to introduce a hat here, and this p hat is just going to be a null vector in space-time that is going to be parametrized by a point on the sphere, so by z and z bar, so it's going to look something like this. And then in general, my p is going to be some scale omega times this p hat. That's only a function of z and z bar. Yeah, thank you for the question. There is a similar thing for massive particles.
This omega would be related to delta.
Yeah, I'm gonna in a moment I'm gonna show. So I'm just gonna focus on the massless case for now. Just I'm going to say some words about the massive case as well. But for the for the m equal to 0 solutions, we have these look very simple. So they are psi delta. There is going to be a plus minus that denotes whether we are talking about an incoming or an outgoing mode. They are going to be labeled by some p hat or sorry, q hat and some ballpoint x. And they are given by the following formula. So just a small comment. You may be very familiar with this formula if you think about the Minkowski, four-dimensional Minkowski space as the embedding space of a 2D CFT. So this is going to look very similar to bulk-to-boundary propagator in some three-dimensional hyperbolic space. And we're going to make a connection to that in a moment. But because, I mean, basically, these Lorentz transformations preserve these hyperbolic slices, so the solution is very natural from that point of view. So basically, we're just constructing some eigenstates of the conformal of the ADS3 isometries, or equivalently conformal symmetries, conformal algebra in 2 dimensions. And it's just a fact that these wave functions are just Mellin transforms of plane waves. So these are just integral from 0 to infinity, the omega to the delta minus 1, e to the plus minus I q hat dot x omega. So this addresses Manu's question. So the Mellin transform, so it's an integral transform that, again, we have seen before. But usually the Mellin transform of an exponential is whatever appears here in the exponential to the inverse of the delta that appears in this formula up to some factors of gamma, which is exactly what we are seeing here. Yes? OK, so that was the next point. So delta, just from what we've said so far, delta should be a continuous variable because delta just replaces omega, and omega is a continuous variable. And indeed, if one just cares about constructing a basis of solutions to these equations, indeed, it was shown by Pastersky and Shao that these wave functions with complex delta, I'm going to write it in a moment, form a basis for solutions to the Klein-Gordon equation that basically check out these conditions A and B that I have listed there. So I'm not going to prove that, but it's actually, it's not that hard. You just have to check, just like plane waves. So they form a basis for the positive frequency modes of the plane waves form a basis with respect to the Klein-Gordon inner product. You can compute Klein-Gordon inner products for these solutions, and you can show that they form a basis. And this was done by Pastersky and Shao in 2017. Well, building on all their work, I guess, also by DeBoer and Solodukin. And essentially, what they have done is they have shown that these psi q delta x of q form a basis of solutions to the Klein-Gordon equations. Equation for m equal to 0, provided that delta is 1 plus I lambda, where lambda is a real number. And sorry, here I should also say, now it's important, you may be worried now. I'm saying delta is not an integer. So this formula actually has singularities whenever x lies on the light cone through the origin. So one has to actually specify a way to regularize that. So one introduces, there is an I epsilon prescription here that I have missed, which is important, particularly for given the fact that delta is not integer. Okay, so what this means is that I can take my on-shell bulk field 5x and expand it in this basis. And so we have an integral over all deltas, since delta is a continuous parameter. And then we have integral over d q hat of some measure mu that I'm not going to write down. And then we have psi of delta q hat x, and then O star delta of q hat plus Hermitian conjugate. And this is a valid expansion for my bulk field. And combining this with the expansion on plane waves that I've written down before, and using orthogonality and complete, really just orthogonality of these wave functions in the plane waves with respect to the Klein-Gordon inner product, one can obtain a relationship between these operators O that appear here and the creation and annihilation operators that appear in a standard plane wave expansion of this field. So let me just write that down. So O lambda, and here delta is 1 plus I lambda. I defined what lambda is, so O lambda of q hat are just defined by taking Klein-Gordon inner products of the bulk field phi with these wave functions. And they turn out to be proportional to certain, essentially, Mellin transforms of the annihilation operators that we may be very familiar with from before. So, so one small comment is that from this formula, so what you can see here is that I can write this as an integral transform of exponential of e to the I lambda log omega, and I can also take a Fourier transform of that and relate this to something that depends on time, and you can immediately kind of see that what these all lambdas of Q do is that they create Rindler or Milne modes asymptotically. So these guys correspond are Rindler or Milne modes. So they would be the things that would appear in an expansion of a field seen from the perspective of an accelerating observer, Minkowski space. And they have also been known as, or like called, conformal primary modes. All right. So given this, given these modes and these wave functions, one can then write down a formula that relates scattering amplitudes in flat space to correlation functions for of primary operators in a two-dimensional conformal field theory. So these are now go under the name of celestial amplitudes. So this is nothing fancy. They are just basically S-matrix elements expressed in space of boost eigenstates. So we have some amplitudes that I'm going to call A tilde, that are functions of the external dimensions delta I, and Zi that are defined as S-matrix elements in this tilde basis, and these are just boost eigenstates. or they're elements of the Fock space version of these boost modes, of these conformal primary modes. And if one wants to write down the map, sorry, again, I'm just writing this down for m equal to 0, and just putting together all the elements discussed so far, one can relate this very simply to a scattering amplitude in the following way. So we have product, sorry, over 1. So if you have n particle scattering, n massless particle scattering, what you're going to do to obtain the celestial amplitudes in the case where the particles are massless is you're going to just take each external on-shell momentum and take a Mellin transform with respect to its corresponding energy. So we have a product over I, from I ranging from 1 to n of integral from 0 to infinity, omega I delta I minus 1. And then we would have the standard scattering amplitude, which is a function of the external momenta omega I q hat I. So any questions? Now, one can do the same thing for massive particles. Just going to sketch how one does that. So in the case of massive particles, one replaces, so these wave functions that we talked before basically take the same form, but one has a different coefficient. There is some kind of Bessel function. And one can use that to find the integral transform that puts the scattering amplitude in the respective conformal primary basis, and it essentially amounts to doing the following. So for massive particles, again, scalars, we replace in the formula above this Mellin transform by an integral over some three-dimensional hyperboloid with coordinates p hat, g delta, sorry, let me put the indices, pi, g delta I, p hat I, q hat, where these are bulk to boundary propagators. On hyperbolic slices. So why this? So the way to think about it is, one thing is that, okay, this comes out of the calculation, but it's very natural why this result comes out. And this is because if you consider, and sorry, my diagram is not, if you consider the light cone through the origin in Minkowski space, massive particles, so we saw that massive particles enter and exit the space-time at a particular retarded or advanced or retarded time, whereas massive particles actually propagate from I minus, so past time like infinity, to future time like infinity. And in particular, the asymptotic momenta that obey p hat squared is equal to, I guess, minus 1. These are just the massive on-shell momenta, are in one-to-one correspondence with points on these Euclidean hyperbolic slices. So the picture is that you can foliate Minkowski space with hyperbolic slices in the Milnor patches and with the Z3 slices in this exterior region, and one can essentially then compute massive celestial amplitudes by summing up all of these contributions from these ADS3 and DS3 slices. Okay, another comment is that, so these were comments A. Comment B is that one can also do, one can also find spinning or higher helicity wave functions, conformal primary wave functions. So for example, photons have conformal primary wave functions that now are also labeled by a by helicity quantum number J, either plus or -1, depending on the helicity. So the +1 is just related to the same massless wave functions that I've written down there via dressing or multiplication with a polarization tensor. So these are the same. This is a component of this null frame that I introduced before. So from amplitude's point of view, it's just a polarization vector. And similarly, there is a formula for gravitons. OK, so any questions about that? Yes?
Yeah, so these primaries that you constructed, they're principal series representations of the global conformal group. Do we know how they organize themselves into representations of the Virasoro group?
That is a good question, but hang on for a moment. I'm going to comment on that in a moment. If I don't, then just please ask at the end. OK, so I'm seeing that I am starting to run out of time. But what my plan was to tell you a little bit how this is related to ADS-CFT and how these wave functions are actually related to both boundary propagators. Not just these ones that we are seeing here in a slicing of Minkowski spacetime, but also both to boundary propagators that would appear in, say, a 4-dimensional anti-de Sitter spacetime. So these things arise very naturally in a flat space limit. And they are related to the story that has been developed in recent years of understanding, or rather, yeah, understanding how this holographic, or how this, how should I say, how this celestial CFT can be obtained maybe from ADS-CFT. Celestial or Carolian field theories can be obtained from Carolian or some kind of higher 3-dimensional conformal field theories in particular limits. Fortunately, I don't have time to do that because I think I should instead connect to the discussion in the previous lectures. I instead want to sketch how to use all of this to rediscover. In fact, this is how it was first discovered, how to discover this W1 plus infinity algebra just from this 2D point of view. Yes?
So far, we have a prescription to compute delta i's from the gravitational quantities.
Yes.
But how do you define what is the three-point function with celestial CFT? How did it be circular somehow?
In fact, the 3-point function of massless particles is singular. And this is just a consequence of momentum conservation. At low points, up to 4 points, you're always going to get singularities. The singularities are related to ballpoint singularities that you would get in 3-dimensional conformal correlators. This relationship has been established. There's nothing strange about them. And they're also related to so-called electric branch of Carolian field theories, if you want, where similarly one encounters the singular correlators. Yeah, thank you. Thank you for the question. I mean, I could have also talked about that. One can obtain that behavior by just studying the constraints on these 2-dimensional conformal field theories from Poincaré symmetry, basically. But yeah. Oh, I'm so sorry. I just realized. Oh, that's awful. I thought I started at. OK, so I only have 2 minutes left. So in the 2 minutes, I'm going to. I'm so sorry. Yeah, OK. OK, so what's the relation to W1 plus infinity? So the relationship is like this. There are conformal primary gravitons that one can write down. And these conformally soft gravitons, they are just conformal primary versions of the soft gravitons that we discussed before. And these are obtained as residues at delta equal to k, where k is a negative integer of basically Mellin transforms of the Fourier transform of the shear. So we have seen this object before. I think I gave you all the ingredients to actually show yourself. So you can do as an exercise, show that these are sub 1 minus k leading soft graviton modes. Okay, and given these operators, one can use minimal input, and the minimal input is the following. So let's define these. Let's call these gk. Right, I'm taking a particular value of delta, and this is evaluated at z and z bar, and they can have one of two helicities. And one can actually write down an operator product expansion for these gravitons, for these graviton modes. I only need one more minute to just sketch this. So there is a 2D OPE of conformal primary gravitons for dimensions, generic dimensions delta 1 and delta 2. So let's take the negative helicity ones to relate to the charges that we've written down before. J2 minus Z2. And this goes like minus kappa, where this depends on G Newton, 1 over Z bar 1, 2. And then we have some sum from n equal to 0 to infinity. And then we have a beta function of delta 1 minus 1 plus n, delta 2 minus 1. So these are like some OPE coefficients. And then we have Z1, 2 to the n plus 1 divided by n factorial dn g delta 1 plus delta 2 Z2 minus plus subleading terms in Z bar 1, 2. And so first of all, a few comments about this. So this OPE is just obtained by just from the leading soft graviton theorem. The n equal to 0 component of this is just the celestial representation of the leading soft graviton theorem. And all of these subleading terms are completely determined by the Lorentz symmetry. Okay, so one can write down these terms just using the only input is leading soft graviton theorem and Lorentz symmetry. And using this OPE, then one can compute the corresponding residues to write down an OPE of soft modes that are going to be labeled by some negative integers, delta 1 and delta 2. And then one can just use 2D CFT techniques to compute the algebra or the commutator of conformally soft, of these conformally soft modes. And upon taking a light transform that I don't really have time to discuss, but effectively that maps a primary to a primary by just flipping the either the holomorphic or anti-holomorphic weight, keeping the other one fixed, one can just recover. So after a little bit more work, one just can show that this commutator actually is nothing but this W1 plus infinity algebra. So with that, we've gone through full circle. It's much simpler. One small comment, this computation is much simpler. It doesn't require you to compute any complicated Poisson brackets of nonlinear quantities. It just involves you doing some contour integrals in a z and z bar. And here you go. So thank you very much.
All right, so in light of the time, we will postpone questions to the break, but this was Anna's final lecture. Let's give her one more round of applause for a nice lecture series.
As a reminder, you've been asked to wait until 1 p.m., please, to go to lunch.